Aloha! Welcome to my presentation. Did neural networks make support vector machines obsolete? In the rapidly evolving world of artificial intelligence, it's tempting to search for a definitive champion among models and algorithms. Yet history repeatedly shows us that the winning approach can shift dramatically when faced with new, more complex challenges. For a long period, neural networks remained in the shadows, sidelined by more analytically appealing models. In contrast, support vector machines, SVMs, rose to prominence, acclaimed for their robust mathematical foundations and strong performance on small to medium-sized datasets. However, the tides began to turn with the emergence of big data, large-scale datasets, and the computational power necessary to leverage them. One of the most transformative moments in this shift came with the launch of the ImageNet project and the subsequent AlexNet breakthrough, which dramatically altered the trajectory of machine learning and computer vision. The story begins with Fei Li, a visionary researcher who came to the United States from China and recognized the limitations of existing datasets in training truly intelligent vision systems. In the late 2000s, she and her team began constructing ImageNet, an ambitious project to compile over 14 million hand-labeled images across thousands of categories. The purpose was to provide a comprehensive benchmark for evaluating the progress of visual recognition algorithms. To further drive innovation, the ImageNet Large-Scale Visual Recognition Challenge, ILSVRC, was launched in 2010. In its initial years, participants primarily employed traditional methods, notably SVMs, often paired with hand-engineered features such as SIFT and HOG. Notably, SVMs were originally developed by two Russian scientists, Vladimir Vapnik and Alexei Chervonenkis. While these models delivered incremental improvements, they fell short of the transformative leap that many in the field were hoping for. Then came the year 2012, a turning point catalyzed by a team led by Geoffrey Hinton, a British-Canadian psychologist and computer scientist, including Ilya Sutskever, a Soviet-born Israeli-Canadian computer scientist and Fellow of the Royal Society, and Alex Krzyzewski, a Soviet-born Canadian computer scientist. Their entry into the ILSVRC, a deep convolutional neural network known as AlexNet, radically outperformed all other models. AlexNet achieved a top 5 error rate of 15.3%, compared to the next best model's 26%, a staggering improvement. This model introduced several innovative techniques: ReLU activation functions for faster training, dropout for regularization, and the use of GPUs to accelerate computation. The success of AlexNet showcased the untapped potential of deep learning, especially when paired with large datasets and modern hardware. It's worth noting that convolutional neural networks, CNNs, themselves were pioneered by French-American scientist Yann LeCun, who integrated the ideas of local receptive fields and shared weights into practical applications, such as digit recognition. The international character of these developments highlights how AI advancement is a truly global effort, bringing together brilliant minds from across continents and cultures. Understanding why neural networks overtook SVMs requires a closer examination of their foundational differences. SVMs are based on the principle of maximizing the margin between classes in a high-dimensional feature space. They rely heavily on kernel functions and are particularly effective when the dataset is not too large and the feature space is well understood. SVMs require careful tuning and often depend on manual feature extraction, which can be both time-consuming and domain-specific. Neural networks, on the other hand, consist of layers of interconnected nodes that can learn complex representations of data. Unlike SVMs, neural networks are capable of automatic feature extraction, allowing them to scale effectively with data size and complexity. Their architecture supports both supervised and unsupervised learning, making them highly versatile across various tasks. The superiority of neural networks in many domains stems from several intrinsic advantages. First, their ability to learn hierarchical features directly from raw data removes the dependency on handcrafted features, which may not capture the intricacies of complex data. Second, neural networks, particularly deep ones, are highly scalable. With the advent of powerful GPUs and distributed computing, training models with millions of parameters on datasets with millions of examples has become feasible. Third, the adaptability of neural networks allows them to excel in a wide range of tasks, from image and speech recognition to natural language processing and game playing. Their performance on benchmarks has not just surpassed traditional models, but has often redefined what is considered state-of-the-art. However, despite their widespread adoption and demonstrated superiority, neural networks have not rendered SVMs obsolete. SVMs continue to hold their ground in several niche but important areas. For instance, in situations where datasets are small, high-dimensional, and noisy, such as in bioinformatics or financial modeling, SVMs can outperform deep learning models. This is primarily because neural networks are prone to overfitting when data is scarce. Moreover, SVMs are computationally less intensive to train for small-scale problems and often require less tuning. They are also more interpretable, a trait that is increasingly valued in fields that demand transparency and accountability, such as healthcare and legal applications. As a result, SVMs remain a strong choice for baseline modeling, and in scenarios where model interpretability and performance on small datasets are paramount. In conclusion, the journey from SVM dominance to the rise of neural networks exemplifies the dynamic and evolving nature of artificial intelligence. While neural networks have shown to be more powerful across a broad range of applications, they have not completely supplanted the utility of SVMs. Each has its own strengths and ideal use cases, and the key to successful AI applications lies in understanding these nuances. The global nature of AI research, with contributions from Russian, Chinese, British, Canadian, Israeli, French, and American scientists, underscores the collaborative spirit that drives progress in this field. As we continue to face new and more complex challenges, it's essential to remain open to the possibility that the next big breakthrough may come from a method currently considered secondary. What are your thoughts? Have you encountered scenarios where SVMs outperformed neural networks in your work? Let me know in the comments. If you found this video informative, please like, share, and subscribe. Thank you for watching. Mahalo.